This week, I wanted to discuss the derivative of the function, which is something that we actually haven't had an opportunity to speak about before. And that's why I thought it would be a good idea for us to be able to do this now. Okay, so the graph that we are going to look at, I'm just going to move this one over actually and then make this a bit bigger. The graph that we're going to be looking at is the graph of f of x equals x cubed minus 6x squared plus 9x. And that is our cubic function. So what I'm going to do is I'm going to highlight this in purple. We know that it's a cubic. And that is this graph over here. All right, so because the value in front of the x cubed is positive 1, it means the graph is concave down and then concave up. So this is our, that would be that one over there. Sorry, it's this line over here. There's our graph of f of x. Then if we take our first derivative of f of x, we get f prime x. This gives us 3x squared minus 12x plus 9, and our parabola is our first derivative of our cubic function. So our parabola is the one in the pink. Let's just highlight that all the way through. There's the graph of our first derivative. And the last graph, let's choose a nicer color than that. We'll go with blue, is our second derivative, which is f double prime x equals 6x minus 12. And this is a straight line. It is the second derivative of the cubic or the first derivative of the parabola. Okay, so let's highlight that. And then we can look at some of the interesting relationships that start to emerge between these three functions. Okay, so we've got our cubic in purple, our first derivative, which is a parabola in pink, and our second derivative of the cubic, which is a straight line in blue. Okay, so the first thing that I want to draw your attention to is the point of inflection on our cubic function. Okay, so the point of inflection is this point over here where I'm putting the little black arrow. There's our point of inflection. What does the point of inflection represent for us? What does the point of inflection mean to us? What's happening here at the point of inflection? On our cubic function, what happens at our point of inflection? Okay, but a change in what values exactly, Lebogang? Think back, Matrix. What happens at the point of inflection?
Check your notes, guys.
Check your notes. Go and look back at all the discussions that we've had. What does the point of inflection mean to us? No, in Nhlanhla. So our min and our max are our turning points, not our point of inflection. What happens at the point of inflection exactly? There's a few things that we can say. So at the point of inflection, there we go, Lebogang, we have a change in concavity. All right, so f double prime x is equal to 0 at our point of inflection. Okay, this is the point at which the graph changes from being concave down to being concave up. Okay, so this is where we get a change in concavity. That's it. Okay, the graph is not stationary at the point of inflection. Okay, Rufenste, the graph is stationary at your turning points. Okay, but not stationary means not increasing or decreasing. All right, so at the point of inflection, f double prime x is equal to 0, and it's the point at which the graph changes concavity. So this particular function is concave down first, and then it is concave up. All right, so it's concave down before the point of inflection, and it's concave up after your point of inflection. All right, so the x coordinate at this particular point is 2. This is what they've told us. Okay, so this is the line x equals 2, this vertical line. And we can see that the x coordinate at our point of inflection is 2. If we look at our parabola, what does that x equals 2 mean for us in terms of our parabola? What's the x coordinate of? What is the x coordinate at the turning point on the parabola? Not a turning point. Yes, sorry, you're quite right, Nhlanhla, the turning point. Okay, so the point of inflection, all right, on your original cubic function, it has the same x coordinate at the turning point on your parabola. Exactly. So not necessarily 0. If you have a look, this seems to be somewhere in the 4th quadrant. Okay, so the point of inflection, or the x coordinate at the point of inflection, is the same x coordinate on your on your first derivative. So at your point of inflection, is the same as the x coordinate of your first derivative. Okay, so in other words, the point of inflection on the cubic and the turning point on the first derivative have the same x coordinate. What is that the same as on the straight line? If you have a look. So that's this point over here, this blue one. What does that represent? Exactly. So it's our x-intercept of our second derivative. Okay, so in other words, the x-coordinate at the point of inflection is the same as the x-coordinate at the turning point on the first derivative is the same as the x-coordinate of your second derivative. Okay, so they are all in the same vertical line, right? What is important to note here is that on the cubic function, when x is smaller than 2 for this particular function, the graph is concave down. The first derivative is decreasing. The second derivative is below the x-axis. Okay, so if you have a look to the left of the line x equals 2, the cubic function is concave down. The gradient of the pink graph, the first derivative, is decreasing. The y-coordinates on the straight line are going to be negative at that time. Does that make sense to everybody? Okay, cool, Nhlanhla. All right, so look at it, look at the picture as I'm saying these words to you. Okay, so when x is smaller than 2, so to the left of the line, x equals 2, okay? The purple graph is concave down. The gradient on the pink graph is negative. The y's on the blue graph are also negative. Okay, to the right of that line, okay, the purple graph is now concave up. The gradient on the pink graph is increasing or positive. The y's on the second derivative are all above the x-axis. They are all positive. Okay, so that's what's important about the point of inflection or the turning point on the first derivative or the x-intercept of the second derivative. Okay, now let's go and have a look at our maximum. Okay, our maximum occurs in this particular example. Our maximum occurs when x is equal to 1. Okay, so our maximum is this point over here that I'm just highlighting in purple. It has the same x-coordinate as one of the x-intercepts on the parabola. Okay, so your turning points on your cubic function are the x-intercepts on your second derivative. Is everybody happy with that? And we'll see the same thing happening with our minimum. Right, so our minimum is here, where x is equal to 3. And you can see that that is the other x-intercept of our parabola. Okay, so the turning points are the same as the x-intercepts on the parabola. Is everybody happy with that? Okay, now the reason why these relationships are important is because they can give you the graph of the first derivative and then ask you questions about the original cubic function. That's why it's important for us to know these characteristics. So, for example, when the graph is concave down on this particular cubic function, the gradient on the first derivative is negative and the y values on the second derivative are negative as well. Or when the graph is concave up, the graph of the first derivative is increasing and the y values on the second derivative are above the x-axis. That is where y is positive. The other thing that they can do is they can expect you to work backwards and find the equation of the cubic function by giving you the graph of the first derivative. So I'm going to show you that now as an example. Okay, that's this particular question over here. Okay, so if we have a look at the one that is in the middle of the screen at the moment. Sorry, let me just scooch over a little bit. Okay. So this particular graph over here, we are told that this is the graph of y equals f prime x. So it is a graph of a derivative and is given where f of x equals ax cubed plus bx squared plus cx, represents a cubic function. The first thing that they want us to do is determine the equation of f prime x. So they want us to determine the equation of the parabola. We have been given two x-intercepts and a y-intercept, which represents another point. What do we need to sub into for the equation of the parabola if we're given two x-intercepts? What form do we use? We've spoken about this before in our previous lessons, and you should know this from grade 11. How do we write the form of the parabola when the x-intercepts and one other point are given? Can anyone remember? Do you recall this formula? Y equals a, x minus x1, x minus x2. Does that ring a bell? Yes, Selma, Lebogang? There we go. Okay, so had you just forgotten about this? You just weren't thinking about it. So the first thing that we would need to do would be to sub in our x-intercepts. So that would give us y equals a, x minus 1 times x minus 2. This point over here, the y-intercept, its coordinates are actually 0 and 12 because it's a y-intercept. So when y is 12, x is 0. So these two brackets are being multiplied together and then by a. So -1 times -2 is 2. So this gives us 2a is equal to 12. Divide both sides by 2 and a would be equal to 6. So when they want us to find the equation of the parabola, we would now have to sub that in. So y equals 6 times x minus 1 times x minus 2. And we would need to multiply all of that out. That would give us, we're going to do FOIL first. So that would give us x squared minus 2x minus x plus 2. Let's remove our brackets. That gives us 6x squared minus 12x minus 6x plus 12. Collecting our like terms, we would get 6x squared minus 18x plus 12. Okay, so that would be the equation of f prime x. Okay, any questions about that one? Mark allocations. So subbing in your other point, getting A is 6, final answer. Okay, Salma. Okay, let's have a look at part pleasure. Let's have a look at part B now. I'll write over here. Now, this is where things start to get a little bit more interesting. Now they want us to determine the equation of f of x. So they want the equation of the original cubic function. So this one that I'm highlighting in blue over here. What they're actually telling us to do here is they're telling us we need to work out the values of A and B and C. Any ideas as to how we would do this? Anyone got a suggestion? What would be our starting point? Remember, we have the graph of the first derivative. So I'm giving you a little hint there. Lebogang, go for it. You're welcome to unmute and speak, Lebogang.
Ma'am,
Mm.
won't we use this 6x squared minus 18x plus 12, and then sub that into the bx squared, cx, and whatever.
You're right that we're going to use the first derivative, so the 6x squared minus 18x plus 12. But we've got to think how that is related to f of x. So what can we do to f of x so that the answer we get is the same as 6x squared minus 18x plus 12?
Don't we look for the second derivative?
First derivative. First derivative, because remember, the first derivative is going to be f prime x, isn't it? So if I've got f of x equals ax cubed plus bx squared plus cx, my first derivative is what, Lebogang? It would be 3ax squared plus 2bx plus c. So these two are the same thing, aren't they? There is your first derivative. Here is your first derivative. Oh, you're having audio problems. No worries. Okay, so our first derivatives are the same thing. It's the parabola that we see in front of us. So now what we're going to do is we're going to look at the first term. The first term of our first derivative is 3ax squared. The first term of our first derivative is 6x squared. So that means that 3a is equal to 6. So a has to be equal to 2. The second term of our first derivative is 2bx. The second term of our first derivative over here is minus 18x. So that means that 2b has to be equal to negative 18. So b has to be equal to negative 9. Good. And the last term of our first derivative is c, and the last term of our first derivative here is 12. So c has to be equal to 12. So that means that f of x has to be the graph. It's ax cubed. So that would be 2x cubed. b is equal to negative 9. So that's minus 9x squared. C was equal to 12, so that would be plus 12x. And that's how we would determine the equation of f of x. Any questions? Again, apart from the mark allocations. So there would have to be a mark for the first derivative, an accuracy on A and B and C. Any questions? We're all good, sure? Lebogang? You're welcome to unmute if you're not having audio problems anymore.
Leborang, you only need to talk. If you are talking, however, we cannot hear you, then it means that something is wrong. But at least you can hear us. Then you can just try and type your question also on the chat. I know it's going to take long. But
Ma'am, can you hear me now?
oh,
I
yes.
can hear.
Now
Oh,
we
there
can
we
hear
go.
you.
Now we can hear you. There we go.
Okay, ma'am, I wanted to ask, could you just work backwards from the derivative? Like if you divide by 2, you still get 3x squared and 9x.
Okay, so what you've got to do, yes, you've got to work backwards, but you've got to take the first term of the first derivative where you have derived f of x, And you've got to make it equal to the first term from part A, which is 6x squared. And because they're both x squareds, because you've got the same variable, you can equate your coefficients. That's where you get 3a is equal to 6 from. All right, and then you would do the same with your 2bx term. You would make it equal to negative 18x, and you would do the same thing with c. So yes, you've got to work backwards. Yes, there was an echo, wasn't there? There's no other way of doing it in this situation, unfortunately. You've got to work backwards. Okay, so I've shown you guys how to use inspection. This is the inspection method. All right, so we're using it here. We're using inspection here as well. All right, let's have a look at the next question that they ask us. They say, by referring to the diagram, so that's the diagram of the parabola, okay, f prime x. By referring to the diagram, determine the values of x for which the graph f of x has its stationary point. So that means its turning points. So this is where you've got to go back, all right, to this over here. Remember, the turning points on the cubic are the x-intercepts of the first derivative. Okay, so I'll say that again. The turning points on the cubic function, those x coordinates there, are the same x coordinates at the x-intercepts on your first derivative. All right, so the turning points on f of x are going to be where x equals 1 or where x equals 2, because these were our x-intercepts on our first derivative. Everybody happy with that? Any questions? Okay, so that would be 2 marks. And the last part, so part D now, they've said to us again, by referring to the diagram, determine the values of x for which the graph of f of x is increasing and decreasing. Okay, so go back and have a look again at the relationships over here. All right, when the graph is concave down, your first derivative is decreasing. When the graph is concave up, your first derivative is increasing. Your cubic function will be increasing to the turning point, decreasing between the turning points, and increasing after the last turning point. Okay, so remember, x equals 1 or x equals 2 are your turning points of your original function, your cubic function. So your original cubic function is going to be increasing when x is smaller than 1. Or it will start to increase again when x is greater than 2. It is going to be decreasing between your turning points. So that is going to be when x is, sorry, I did the wrong thing here. No, that is correct. Sorry, that is correct. So it's going to be where x is greater than 1, but smaller than 2. Is everybody happy with that?
Ma'am, wouldn't we have to include the x's because they're on the graph? They're points on the graph.
No, but they're asking about increasing and decreasing.
Okay,
So
ma'am.
you don't include your turning points when you're talking about increasing and decreasing. Remember, we are not talking about the graph that we see in front of us. We're talking about the cubic function.
Okay, ma'am.
Okay. Any other questions? Is everybody clear on that? Are you sure?
Yes, ma'am.
Okay. Is this maybe easier than I'm making it out to be? All right. So for inequalities, there can't be part marks. All right. There would have to be that, and then that would be out of 2 marks. But this is just a different way in which you can write it, but you can't using interval notation. But you can't do anything different there. Okay, you sure there's no other questions? Okay, so screenshots, everybody. Take some screenshots. Yes, so Leanne, I've got another question here for you. Okay, so here we go. So here is the graph of the first derivative. It represents a cubic function, which is not sketched. That is the graph f of x equals ax cubed plus bx squared plus cx. This is the graph of the first derivative. So just like the previous question, the first thing that they want you to do is to determine the equation of the first derivative, f prime x, and the original cubic function, f of x. Let's see if you guys can do that. Okay, because it's identical to the previous question. The only difference is that when you calculate the value of a, and I'm talking about this a over here, just highlight it in blue, this a over here, you're expecting it to be negative. Remember, this graph was smiley face. So we expected the number in front of the x squared term to be positive. Here, it's going to be negative because the graph is sad face. All right, so let's see what you guys do there. I just want you to do part A, and when you're done, say done in the chat. Cool, Nhlanhla. And have you found the equation of f of x as well? Not just f prime x. Cool, Gugu, well done. Good, Elratile. Good, Lebogang. If you want to, you're welcome to try questions B, 1 and 2, and even question C if you like. We'll just give the others some time to catch up. Good, Charmaine. Good, Aura. Good, Capano. Okay, anybody prepared to share an answer with us? What did you get for f prime x? Anyone prepared to share an answer for their solution for f prime x? Don't be shy, Matrix. We all make mistakes. Don't be scared to share your answers. If you do make a mistake, it's a good thing because then you can figure out where you've gone wrong, which helps all of us. Don't be shy. What did you get for f prime x? Nhlanhla, do you want to share your answer? What did you get for f prime x, Nhlanhla? Kapana's sharing her answers. Okay, I also got, so Kapana, I'm sharing some of my answers with you. I also got negative 3x squared. I did. My middle term was different though. So your first term is perfect, Kapano. So we're talking about f prime x. Here I got plus 12x, and then I got plus 15. Do you guys get the same answer as me? For f of x, I got negative x cubed plus 6x squared plus 15x. Yes. Did you guys get the same answer for f of x, the green? Yes, you all got that. Okay. Good. Maybe you're just feeling shy this evening or tired after writing exams, etc., etc. All right. Is there anybody that didn't get those answers who wants me to do that for you? If you did get it, then we can move on to the next thing. Okay. So Copano, which you would have just done very quickly. The rest of you, if you want to carry on with B1, 2, and C, you're very welcome. I'm just going to show this to Copano again. Okay, so Copano, what you would have done here is you would have subbed into y equals a, x minus x1, so that would give you x plus 1, x minus 5 when you sub in your x-intercepts. Then you've got to sub in your y-intercept, so that's 15 when x is 0. All right, so 1 times negative 5 times a is negative 5a. And that would be equal to 15. That's why a is equal to negative 3. So that's this negative 3 over here. Then you've got to take that and go and sub it back into the first line. Y equals negative 3 into x plus 1 into x minus 5. Okay, so once you have foiled out your brackets, you could multiply through by the -3. So that gives you x squared minus 4x minus 5. And removing your brackets, you end up with -3x squared. That's where I got plus 12x plus 15. Okay, so that's where you can see it's the same as the pink one up there. Okay, Capano. I'll just move down and show you that again. All right. If there are no questions, let's have a look at part B. Okay. So in part B, for which values of x will the graph f of x, now remember this is your original cubic function. So remember it's first going to be concave up and then concave down. This over here is -1. That over there is 5. Okay, so for which values of x will it be increasing? It will be increasing between your turning points. So where x is greater than -1 but smaller than 5. That's part 1. Where will it be a decreasing function? That will either be where x is smaller than -1 or where x is greater than 5. Okay, it helps a lot, I think, to draw the little cubic function over here so that you can compare the two. Okay, when you answer these questions. At which points will the graph have its turning points? That's part C. Remember, the turning points are the same x coordinates as the x-intercepts of the first derivative. So it has its turning points where x is equal to -1 or where x is equal to 5. Okay, so Leanne, you said you wanted to do another question, which we've done because this was a little bit confusing. How do you feel now, Leanne? Is it starting to make a bit more sense? Any questions, Matrix? You're okay now. Okay, so the idea, let's just see, there's another person in the chat. No problem, Leanne. Okay, so Matrix, when your cubic function is concave down and then concave up, okay? So this would be f of x. Your first derivative is going to be a smiley face. Your second derivative is going to be a straight line with a positive gradient. If your graph is concave up and then concave down, your first derivative is going to be a sad face parabola. Your second derivative is going to be a straight line with a negative gradient. Does that make sense to everybody? Yes, Lebogang.
Ma'am, can I ask, when will the
Of
straight
course.
line become a constant?
What do you mean when the straight line becomes a constant?
I think, I'm not sure, I think our teacher said when you take the second, you do the third derivative, it will become a constant.
Yes, it would be. Yeah, absolutely. So if you took another derivative, but you don't need to do that for the CAP syllabus, okay? Because if we go and use one of these that we have as an example here, we could even go back to this one over here because we've got we've got the original, we've got the first derivative, we've got the second derivative. So if you took a third derivative here, okay, which is beyond the scope of what we would need, you would end up with that. So that would be a straight line. Okay, so then it would be a straight line that's horizontal. Okay, but you don't need to worry about that. That's beyond the scope of CAPS.
Oh, thank you, ma'am.
All right, no problem. Kapano, what do you want me to repeat? What I was saying here.
Yes, ma'am. The concave up and down thing.
Okay, all right. So if your graph, so in the case of the green, let's write in the same colors. If you've got the graph of ax cubed plus bx squared plus cx plus d, for the ones that are green, here a is positive. For the blue one, here a is negative. So the number in front of the x cubed. So in the case of the green graph, up to the point of inflection, the graph is concave down. So where I'm drawing the blue highlighting, the graph is concave down. Now where I'm doing the purple, then it becomes concave up. All right, so if your original cubic function is concave down and then concave up, your first derivative is always going to be a smiley face parabola, because here, when you're talking about f prime x equals ax squared plus bx plus c, this a is also positive. With your second derivative is in the form y equals mx plus c. So here your gradient is positive. With these other ones over here, your original cubic function is first concave up to your point of inflection. Then it's concave down. So your first derivative is a sad face parabola. And your second derivative is a straight line with a negative gradient. Okay, so the other thing, okay, no problem. The other thing that you need to remember, your point of inflection, that x coordinate is the same as the x coordinate at your turning point, is the same as the x coordinate at your x-intercept if this was the x-axis. Okay, so same story over here. The x coordinate at the point inflection is the x coordinate at your turning point. And again, if that's your x-axis, that would be your x-intercept. Okay, your local maximum is going to be that x-intercept over there. Over here, your local minimum is going to be this x-intercept over here. Okay, so the turning points, the x coordinates at the turning points on the cubic function are the same as the x values at the x-intercepts on your first derivative. Okay, is everybody happy with that? Any questions? You all good?